Good morning. Welcome to PDC. Thank you all for attending this year. I'm really excited today to present to you the Windows Azure platform and how we host and maintain the lifecycle of your services. My name is Eric Smith. I'm a development manager. I work on the Fabric controller, something I'll tell you about today. Presenting with me today is Chuck Linsmeyer, an architect on our team. So let me tell you a bit about how this talk will be structured. In the beginning, I'm going to introduce you to the Fabric controller, talk to you about what it does, what it is for, how it helps maintain your service. I'll also introduce the service model. This is how you describe to us what you want the Windows Azure platform to do on your behalf. And finally, we'll give you some insights into how all this works. In the first part of the talk, I'll present at a macro level and talk at the data center level what we're doing. In the second half of the talk, Chuck will talk about what we do. He'll zoom in on a particular machine. So let me talk briefly about what goes into deploying and maintaining a service today. Step one, you have to provision, find a set of machines, allocate machines. You may have the machines already in an IT department or in a data center, or you may have to go out and procure new machines. When you find those machines, it's not just a matter of saying, hey, I have a machine here. You have to make sure those machines are scattered appropriately around your data center. For example, you want to avoid any single point of failure. Additionally, you want to make sure that those machines have the resources required to host the various roles of your service. So they have enough CPU, enough storage available, enough network bandwidth to talk to the other roles, low enough latency depending on who they're talking to, that sort of thing. Once you've identified that set of resources and you have the appropriate hardware, you then have to provision that hardware. Install operating systems, configure things the correct way, install your application bits, etc. Not only do you have to provision the machines, you may have to provision the other networking hardware. So set up your load balancers, have it set up to probe and route it appropriately to all your front-end roles, for example, or set up DNS entries, virtual IP addresses out on the internet, that sort of thing. Once you get your service deployed, there's a constant maintenance that goes on. You're going to want to fix bugs. You'll add features over time. So you need to upgrade that service. Anytime you upgrade the service, you may have to go back and revisit those earlier steps. For example, when you upgrade your service, you may decide, hey, we just need to make it bigger. So you have to go allocate more machines again. You also, as you update the code, or maybe the underlying operating system, you'd like to do it in such a way that your service can continue to run. So today, people have to manage all that complexity themselves. And finally, unfortunately, when you're working on a service of any scale, there's going to be failures. Occasionally, hardware is going to fail and have to be replaced. Software itself may crash. Machines may blue screen, whatever. And you're going to have to recover those. So there's an ongoing monitoring and maintenance of your service that has to happen. The Windows Azure platform basically attempts to automate most of these steps for you. So let me talk to you basically how this is done. The component of this system, we've referred to Windows Azure as an operating system for the cloud. The component of the system that manages and makes these types of decisions and drives the automation is the Windows Azure Fabric controller. Like any other operating system, the Azure platform basically abstracts your application from the underlying hardware. So you don't have to know necessarily what machines you're running on anymore, or the fact that you're in a VM or not in a VM. You don't have to know necessarily there's a load balancer distributing the traffic to your front-end roles. In reality, there may be, but you don't have to know. You're removed one level back from that. The Windows Azure platform, like an operating system, has a driver model. So it's easy for us if we support a certain switch, for example, or a certain load balancer. We'll program it, but we program it through drivers. And when new load balancers come out, the way our model works is we'll have a new driver for that new load balancer. So again, we very much follow the pattern of an operating system. As far as managing the hardware, we have a pool, an inventory. You'll hear me in the talk repeatedly refer to this as essentially the Fabric controller maintains a graph, essentially, of the inventory that it manages. And in this graph, each of the nodes could be a computer, a load balancer, a switch, a router, a network management device, what have you. And each of the edges of this graph are networking cables or power cables or serial cables. And that is the inventory that the Fabric controller manages and controls and will later use to host your applications. We can take hardware from the raw, powered off state, powered up, completely provisioned as needed. When we provision a node, we might decide to dedicate an entire machine to a role, depending on the resource requirements of that role, or we may partition a machine into VMs. The way the Fabric controller knows what to do and how to provision the hardware for your service is via a rich service model that you will describe. This is basically a declarative model that includes the type of information you normally might provide to an IT group that might be deploying your service for you. So it basically uses this rich declarative model to map your service onto the pool of shared resources that it has. Similar, again, to how a normal operating system will run multiple applications within the same address space, right, or the same chunk of memory. And then the Fabric will then maintain the life, deploy, maintain the life of that application, and maintain any SLAs that are specified. So what's special about all this really is the model-driven environment, that we have all the information. You've essentially provided us with all the information we need. You've told us how to deploy your service, what the needs are, and how to keep it healthy over time. So let me talk a little bit more about this service model and what's included in there. At the highest level, the service model lets you describe the topology of your service. So I already mentioned the inventory that we maintain is essentially a graph. Your service model essentially also provides us a graph representation of your service. So if your service has various different roles, and by role I mean a process or maybe a group of processes that work together to do a common task, right? So for example, a front-end role for your application. You may also have a back-end role, or maybe a role that does some sort of caching. But in your service model, you describe what those various roles are and how they're linked together. Which roles communicate with what other roles, perhaps what interfaces you expose out onto the internet or to other services within the environment. Additionally, for each of the roles in your service, you can define various attributes. So for example, you can describe what the hosting environment to host that role might look like. Some roles might need IIS. Another role might need ASP.NET. Another role might just need the CLR, but it doesn't need anything else. You can also describe how much resources you need. How much CPU, how much disk. What are your network requirements? What kind of latency and bandwidth do you need as it relates to communicating with other roles? Finally, you can define things such as fault domains. I mentioned earlier that when you allocate or find resources within an existing data center, you don't want to all grab a bunch of machines on a single rack, for example. If you did, a single switch failure might take your entire service out, or a single power failure. So you might want to scatter things around. You can also, in the model, describe how many instances of various services you want. Let me talk a little bit more about fault and update domains. I just alluded to it, scattering your role instances around such that they're not all in the same place. You'll want to, based on that graph I mentioned, the topology, the inventory that the Fabric maintains, that Windows Azure maintains, we can derive various fault domains. For example, if we have a single edge in our graph, a network link, connected to maybe a top-of-rack switch for a rack, well, we know if that switch at the top of the rack goes out, all of those machines behind that rack will lose their network connectivity until that device is replaced. So we can derive what these points of failures are, these single points of failures are, and statistically we can model what the likelihood of various failures are. However, in your application, you might know that your algorithms assume, hey, I need to have at least 3 redundant copies of some piece of information, right? In which case, you'll want to put those roles across 3 different fault domains, for example. An upgrade domain is a similar concept. A fault domain is an area, like I said, is anything behind a single point of failure, right? An upgrade domain is a little bit different but orthogonal. It's a similar idea. When we do a rolling upgrade of your service, when we're updating your service, we might take a certain percentage of it offline at a time. And by specifying update domains, you're basically telling us what percentage of your service can be brought offline at a time. In practice, both of these things could happen at the same time. We may be in the middle of upgrading your service, have a particular upgrade domain offline, and then a fault happens at the same time. So we strive to make sure that things are scattered around and these things are orthogonal. You can think of a fault domain as being perhaps a rack, and upgrade domains scattered across racks, so that you could survive both of these failure types at the same time. So going back to the service model, some of the other things that we let the user specify in this service model are not just the topology of the service, but various configuration. Okay? So there's kind of two roles that will be followed in general. There's the author of the service, who kind of defined it and maybe was involved in writing the code. So he knows, hey, when this role instance runs, it's going to want to have certain information. Imagine, for example, a setting that says what the background color is for a web page, as a simple example. There's a second role, which is the deployer of your service. So the deployer of the service can fill in these configuration settings at deployment time. And that way, your service can be authored in a way that you can easily deploy different configurations or change those configurations easily and rapidly as upgrades to your service. There's different types of configuration settings. There's a type that you create yourself. You can have all kinds of application settings. And there's well-defined system configuration settings. So the system configuration settings refer back to the number of fault domains, update domains, the number of instances of roles. The application configuration settings are basically anything that you want and that your application needs. All of those settings are available at runtime to your role. So in the PDC, I'm kind of alluding to how things work. This rich service model exists. In the PDC release, in the CTP we're handing out and letting you guys play with, we don't expose the service model directly. Instead, there's a number of plugins in Visual Studio or predefined templates. So you can pick a simple model that you want to derive from, and then the model will get generated for you on the back end. Over time, we'll expose more of the full richness of the model. But for now, it's pretty simple. So this illustration basically shows you might pick a simple template that has a front-end worker web role and a back-end worker role. And it kind of gives you an example of what the underlying service model would look like. So let me talk briefly about the steps in deploying the service. I don't know how many of you have already gone out to the Azure.com and tried deploying a service. I've seen the statistics each night of how many people have done that, and I know several of you have, but I know a lot have not yet, so I hope you all will. But the basic model, how this works is you write your code, you get your code working and done, and then at the point where you go deploy it, you'll submit your model and your code up to the portal. It will be deployed, and we'll basically tell you, can we satisfy the needs of your model or not? Right now, we've gone to great pains to make sure we'll be able to satisfy anything that you guys can generate with the models that we've given you. So you won't ever have it tell you no at this point. At that point, the system itself will go provision, and then all the deployment and driving machines to the goal state and keeping the service healthy are all automated. Right? So we basically have tried to take all those steps before and make them all easy. So what I'd like to talk to you now is how the system actually does that. Go into a little bit more detail of how we drive, how we do all those steps I talked about before. So as far as the resource allocation goes, we have a big pool of inventory, right? A shared pool of resources where we'll deploy all of your code. And when we make decisions on what to deploy, we'll consider we'll take lots of things into account. I'll talk about all that in a minute. Then we'll go and provision. You don't have to worry about it. It's all automatic. We will give you mechanisms to do upgrades. It's basically push button. You say, here's my new code, and go. And then finally, the system itself will monitor the code and the underlying hardware to keep your service healthy. So what goes into finding the resources for your service to run in? At the end of the day, this is basically just each role instance described on your model, we need to find a node to run it on, right? This is essentially a big constraint satisfaction problem. So we'll take the various nodes. Again, I described them both as graphs, right? And the nodes in your service model are role instances. The edges in the service model are the communication channels between them. So we'll take that graph and overlay it on top of our inventory and try to make sure that each role instance maps to a node that can host it, that has the appropriate hosting environment, that has the appropriate resources remaining, that's in the right fault domain, in the right upgrade domain, etc. We won't always give you an entire machine. In fact, for the PDC, we never will. We'll always put you in a VM. So we'll sub-partition the machines. And our resource allocation is done basically as one big transaction. It's kind of an all or nothing thing. So let me talk a little bit about how this step actually worked. I referred to it as the graph. I want to show you the connection point. And understanding a little bit more about how this works will make the next thing I talk about make a little bit more sense. So basically, we have a couple of data structures internally that help us track the state. The items in red here essentially came from the service model. This is what was provided by you. So we have a description of the service, various attributes for each role, and then things that are particular to a role instance. The items in blue across the top, the darker blue, are basically our runtime mappings to those models. Okay? So at the lowest level is this notion of a logical role instance. And that's the thing I said before. For each logical role instance, we're going to want to associate it or bind it to a logical node. That logical node is basically our representation of the hosting environment or the machine or the VM where we're going to host you. And it's connected to a physical node. Here's a zoomed in example. Based on the logical nodes that we connect to a machine or logical role instances that we connect to a logical node, that implies or derives a goal state for that machine. So as soon as we bind a role instance from your node, from your service to one of our nodes, that instantaneously, as soon as it happens, has essentially changed the goal state for that node. So the fabric now, in parallel across all the machines, can start driving that node into the new state it needs to be in to host your service. The other state that we store for each node is basically the current state. And we keep that up to date by communicating with the physical hardware. So once we've decided what roles are going to run at each various location in your service, we start provisioning those machines. The way that was done internally is by making that binding between our logical node infrastructure and your role instance. So now at this point, we essentially have a state machine for each of these nodes in the data center, for each of the components. And we'll try to drive all of them into that goal state as derived by the bound role instances. So at periodic times, we'll either periodically pull the physical hardware, or we may essentially get interrupts, notifications from it. And at any point in time, we'll update our cached belief, and we'll decide what is the next step we need to take to drive the state of that node into the state defined by the goal state. And this happens very much in parallel. We can roll your service out very quickly because this happens across all the machines in the data center at the same time. They're all autonomously moving forward. I was just referring to your role instances and how they combine to nodes in our data center. But that's not the only thing that we're configuring. We also have to go and configure the various networking hardware. We have to allocate IP addresses and associate those with a load balancer. Maybe configure a load balancer to listen to a certain IP address and distribute traffic across all your front-end roles. So we'll go program the load balancer appropriately. We could do a couple of things. When we set up the the dedicated IPs, all the IPs that make up the pool that back your virtual IP, will do two things. One is, when we initially create those dedicated IPs, we put them into an out-of-service state. So by default, the load balancer won't initially send traffic to any of your roles that haven't been started yet. As those roles start up and the Fabric knows they're running correctly, we'll now tell the load balancer, hey, that dedicated IP is in service, and the load balancer will start forwarding traffic to that role instance. So they can all come online at different times, and the load balancer will behave appropriately all along the way. Additionally, we program the load balancer to probe the various nodes so that if a machine dies, even before the Fabric finds out about that, or if your role instance crashes or whatever, the probing will tell the load balancer to stop directing traffic there. Additionally, we'll set up routing information on all the machines so that any of the traffic you do, either communication with other roles or communication with the storage subsystem or communicating with something out on the internet, can be routed appropriately. And like I said earlier, we build a lot of redundancy in the data center. So even if there are certain failures, a load balancer fails, for example, there's a redundant load balancer that we programmed the same way that can take up the slack. Once your service is up and running, the Fabric controller also aims to keep it running. So like I said before, in a service of this size, bad things can and do happen, right? So for example, a role can die. It just crashes, takes an exception, and dies, right? A role could also tell us it's unhealthy for some reason. Maybe for whatever reason, you just can't behave appropriately, and you can tell the Fabric about that, the Windows Azure platform about that. When the system learns that your role is unhealthy for whatever reason, we update the state of that node. Okay? That current state in that logical node I told you before changes, and it no longer matches the goal state. So we can now take action to drive that node back into its goal state. So for example, if your role crashed, we can restart it. Right? If the underlying hardware failed, we could take steps to either try to recover that underlying hardware or, if we can't quickly recover it, move your role instance somewhere else. Okay? So your service continues to run. And then we can go at our leisure and replace the bad hardware, for example. So how do we do upgrades? I've mentioned before, you want to keep your service up and running as we upgrade it. In some cases, you might not want to upgrade your service at all, but we might know we need to patch the underlying OS. Maybe it's one of the monthly patch cycles, and we have some new patches we have to roll out. So we need a way to be able to update your application if you wanted to update it, or the underlying OS if we needed to change it, but keep your service online. So basically, the way this is done is basically a rolling fashion. You can think of a wave that goes over your service. And we basically take offline some percentage of your service at a time. So in the topology of your service, for each type of role, you've described to us how many update domains there are, which essentially describe how many stages in that wave there are. And we'll go one stage at a time and take that stage offline and then bring it back online. When it's completely up and running again, move to the next stage. Take things offline, bring them online. And we'll do that rollout for you. There's actually two ways this process can work. There's a manual upgrade where a human determines when it's safe to move from one wave to the second. And there's also basically automatic. For your services, we basically just do an automatic upgrade. So for some of our own internal things, we do manual today. Rollbacks are handled basically the exact same way. So what actually happens, I showed you before kind of that graph a few slides back where you had the mapping of your service that mapped to some internal logical data structures on our side. What we do is when we do an upgrade for you, we create a new instance of your service with your new settings, your new data structure, your new code, whatever. But it's not bound to the nodes yet. We've made the decisions about what's going to live where, but we haven't bound it yet. As we go through each wave, we basically disconnect the old version of the service, connect the new one, which has the side effect of changing the goal state for that logical node. Right? When that goal state changes, we'll basically do the minimum of what we have to get back to where we wanted to be. What this means is, if as part of your update, the only thing you changed was a configuration setting, and maybe you only made that configuration setting for a particular role type, and your other roles weren't affected, it basically means the upgrade is instantaneous for your other roles. And for the role that did have the config setting change, the only thing that changed was that one config setting. So it's very quick and easy for us to drive that machine into the goal state again. We just tell the node, it can still be running. We tell the node about, or the role, about the new config setting. Your role might say, hey, I can handle it, great, and we don't even shut you down. Or you might say, you know what, I can't handle that config setting, in which case we'll shut your role down and restart you quickly. But this all happens in a matter of seconds, right? In another case, you might say, hey, I actually need different code. I'm pushing down bug fixes or new features. In that case, it'll be a little bit longer. We'll deploy to all of your machines in parallel the new bits before we even start this. But then we'll take that one role offline and then just restart it with a new bit. So again, it's pretty quick. And in the worst extreme case, you've actually said, hey, you need different resources, and we have to move you to a different machine or a different hosting environment. We have to lay down a new OS. And it'll take a little bit longer. But in general, everything's automatic, and it happens as quickly as it can. So I've kind of talked about how we maintain your service. We also have to maintain the data center in general. So in general, even if you haven't deployed a service, even today, maybe in your enterprise, you're deploying a service, and you've worked with your IT department on things, and the things you communicate to them are the types of things that today you communicate to us via your service model. But that IT department's doing a lot of other things that you don't even know about or worry about or care about. We take on those same burdens in our data center, right? But again, it relieves you from having to worry about it. So, for example, we'll have to make sure that we burn in new machines before we ever deploy someone's role to it. We want to make sure the hardware is working as expected. If a piece of hardware fails, we'll go run diagnostics on it, and we'll have people remove those machines, fix the failed components, and put them back. So all of the RMA processes happen automatically. A big thing, probably one of the biggest value propositions of a platform like this, is that capacity planning is something you don't have to worry about. In general, what we found inside Microsoft as we talked to other big services that have deployed internet scale applications is that it's very, very tough for them to do capacity planning. And things may change very quickly that change the capacity they need. For example, a news story might increase the traffic going to live.com, right? Or MSN, or live search, what have you. So with a platform like this, using a shared resources, all you have to do is come along and say, hey, I need more capacity. And then it's our burden to make sure that capacity is there. So what about security? If you're going to run in a shared environment like this, you need to know that your service is isolated from other services and that it's safe and secure. So we strive to provide a secure environment by taking a number of steps. First of all, we isolate roles from each other with VMs. Additionally, at least in the PDC offering, we require that your code is managed code, which allows us to run it at certain trust levels. I mean, essentially, managed code allows us to set up a sandbox, right? So we can use code access security. We can run you at a reduced privilege. Additionally, we'll set up various firewalls, right? Each of the machines are configured to only allow incoming traffic that it expects. So if a VM, for example, is expecting to get traffic from only another role that you provide, that's the only traffic that will be able to come in. We also set up IP filtering, and like I said, we use VMs. So this allows us to isolate your role and your service from other roles and other services in this shared pool. Additionally, we'll take on the burden of applying the latest security patches whenever those come out. And we'll roll those out in a quick, rapid fashion. So let me talk a little bit about the Fabric controller itself and how we keep this a high level of availability. So the Windows Azure Fabric controller itself is made up of a basically a cluster of 5 to 7 machines. The state that we maintain, this isn't your state, but it's our internal state about what services we've deployed and what machines they're on and what the state of the various nodes are. This state is replicated across all the nodes in the cluster. So if a single one of our nodes fails, we can quickly bring up, fail over, so to speak, to another one of these nodes who can take over. Basically, a new primary will be elected quickly. Even if all of the nodes are down, however, should never happen, but even if it is, the system is architected so that the deployed services will continue to run. So we could take the Fabric Controller or the Windows Azure platform essentially offline in a sense, and your services continue to run. When we upgrade, the Fabric Controller bits themselves, they are done the same way that your code actually works. In fact, what we actually have is we actually have a tiered level. So the Windows Azure Fabric Controller is running and is deploying your services. We actually have a smaller instance of Windows Azure with a smaller pool of resources that it maintains that deploys Windows Azure as a service. So we have all the same techniques. Our Fabric Controller is deployed across a number of fault domains. It can be updated in a rolling fashion, et cetera. We also, in an effort to keep availability high, we also take advantage of the redundancy and the networking gear. Again, scattered things across fault domains to avoid single points of failures. And even in a disaster scenario, we periodically checkpoint our state. So even if we lost everything, we could rebuild it quickly. So overall, we have tried to provide an environment where the life cycle of your service can be maintained automatically. In the PDC release, we're not exposing all of the richness of the platform to you directly. You do get the automated deployment and lifecycle management, but we don't expose the full richness of the service model. Instead, that's abstracted away slightly by the templates we expose as the Visual Studio plugins, the models you can pick there. We do have support for adding and removing role instances. You specify the various update domains, or we honor update domains. You can upgrade and downgrade your service. We will maintain and recover nodes as they fail, keep your service healthy. We'll do all the external network programming the VIPs, doing the DNS entries for you, that sort of thing. We do all the isolation I described to try to maintain a secure environment, and automatically handle the hardware management. During the next calendar year, we'll try to make this richer, give you more types of roles, for example, be able to deploy unmanaged code, for example. So have a richer set of offerings. So in summary, we try to automate the life cycle of your service, take away a lot of the common burdens that everybody has to do over and over and over again, but keep you in control. You describe what you want via the service models. We strive for a very secure, very highly available environment. This is a community tech preview at this point, so we may not achieve that, but that's the goal. And then obviously we do all the behind-the-scenes data center management. So what I'd like to do next is to invite Chuck Linsmeyer onto the stage, and he will go into depth onto what happens on an individual node. Thank you.
Thanks, Eric. Good morning. I am indeed Chuck Linsmeyer. I'm an architect on the Windows Azure operating system team. I've been with Microsoft since 1989, dating all the way back to the original Windows NT team. Eric has talked about how the Fabric Controller manages compute nodes in the Fabric, assigning compute instances, role instances, to nodes, and then monitoring and managing their health. He also mentioned that we deploy to virtual machines. I'm going to talk about these virtual machines, how we deploy them, and about how virtual computing allows you to deploy your services quickly, reliably, and at lower cost. So one of the primary design tenets of Windows Azure is to maximize server utilization in the data center through multi-tenancy while maintaining strong security and performance isolation. Now that's quite a mouthful. Maximize server utilization. What we have found in our data centers, and we have anecdotal evidence that this happens in other places, is that the average server utilization is extraordinarily low. We're talking numbers well below 50% in many cases. And as the power of commodity server hardware increases, this problem only gets worse. So we need to find a way to drive up that utilization. Multi-tenancy is a way to run, is the idea of running multiple services on a single host. Doing this allows us to improve the performance per watt per dollar ratio by running more services on less hardware. This lowers both capital expenditures and operational expenditures, CapEx and OpEx. We can share resources and manage power consumption more effectively. Now, running services together on the same host obviously has security concerns. Using virtual machines helps deal with those concerns by providing the same security isolation guarantees that running native would provide. And it does it in a way that's reliable, inexpensive, and transparent to applications. I guess I forgot that. Virtualization also allows the fabric controller to have a more idealized view of the hardware. When it's deploying a virtual machine to a physical node, it doesn't need to be aware of all the physical differences in the hardware. This increases operations automation and lowers OpEx. Virtualization in Windows Azure is hypervisor-based, with a microkernel type hypervisor managing the virtual machines as well as the host OS, which provides services to the hypervisor and to guests. The hypervisor model provides efficient and scalable virtualization and also allows us to leverage advances in processor virtualization assist features. This diagram shows the high-level architecture of hypervisor virtualization in Windows Azure. You can see two guest partitions here. These are virtual machines running instances of Windows Azure applications. You also see a host partition. This is the host OS, which really is a partition. Technically, it's a virtual machine just like the others, although it's special in that it has access to the physical devices in the machine. The hypervisor, shown near the bottom, controls all of these partitions. It manages the logical processors, the cores in the machine, scheduling virtual processors from the partitions, the virtual machines, onto the logical processors. Scheduling is one of the key performance considerations in the hypervisor, and I'll talk more about that later. The VM bus is an optimized conduit for communication between the partitions and between the partitions and the hypervisor. I/O traffic is one of the kinds of traffic that passes over the VM bus. The virtualization stack provides optimized I/O by placing virtualization-aware drivers in the guest operating systems. The Windows Azure virtualization architecture is highly optimized for our data center environment. As I mentioned, it leverages hardware features that are critical to our virtualization strategies and to our performance goals. We've optimized every virtualization element on that diagram: the hypervisor, the VM bus, the virtualization stack, the host OS, and the guest OS. I'll talk a lot more about virtualization in a minute, but let me step back and talk about deployment. Because, given that we're deploying into virtual machines, it's natural to think that we would use virtual hard disks as containers for the operating system, and that, in fact, is what we do. the Fabric controller assigns a role to a node. We send an operating system in a VHD to the target node, the host node, and start up the virtual machine using that VHD. Now, the key thing about the way we do this is that we build these OS images offline in an entirely automated fashion. We don't install the operating system at target nodes. We build an image of the operating system offline, configured exactly the way we want it to be configured, and when we send it to the target node, it's ready to go. It's boot and run, quick and painless. When we want to service the operating system, we do not do it by sending an update package to thousands of nodes and having each node run that update package separately. Doing this would be slow and unreliable. We found in our data centers, for example, that that kind of an update model leads to a situation where you're not sure really which nodes have successfully applied which patches. So what we do instead is we service the operating system image offline. Just as we build the image offline, we service the image offline in an automated way. This allows us to verify that the patches have successfully been applied to the image before we send it out to the data center. We keep application and service images separate from the operating system. There's a few reasons for this. First is we don't want to maintain a variety of combined operating system and application images. Another is we want to be able to update the operating system separately from the applications. And the third is, in order to anticipate demand, we want to be able to deploy the operating system to virtual nodes and have them ready to go when the Fabric controller assigns a compute instance to a virtual machine. Now, using virtual hard disks is perfectly natural and understandable for virtual machines. But the question then becomes, what do we do to deploy the host OS itself? Well, we do that in Windows Azure exactly the same way. We build in an OS VHD containing a hypervisor-enabled image of the operating system, deploy that to the node, and then boot the node natively from the hard disk. We added this feature to Windows Server 2008 as part of the Windows Azure project. If you're at the keynote on Tuesday, you heard that the Windows team liked this feature enough that they've added it to Windows 7. Let's walk through a deployment scenario. Here you see a raw, empty node in a blade somewhere in a rack in the data center. All it has is a BIOS that knows how to boot from the network. So the first thing we do is download, remote boot a maintenance OS. You can think WinPE here. An agent that we've added to the maintenance OS knows how to find and talk to the Fabric controller, which tells the agent to set up a host partition, prepare the hard disk on the machine, and set up a host partition to hold the host OS and the hypervisor. The next thing we do is the agent downloads the server core, a hypervisor-enabled server core VHD. Next, we attach a differencing disk to that VHD. This allows the base VHD to be read-only, with all changes going to the differencing VHD, which in turn allows us to reset to a known state if necessary. Those two boxes, there are really two boxes on the hard disk of the machine. They're two files. Next, the maintenance OS shuts down and the machine reboots into the operating system, booting natively from the VHD. Again, an agent inside the operating system speaks to the Fabric controller. The Fabric controller says, let's set up a virtual machine, a guest partition. Again, we download an operating system VHD. For this example, it's a Server Enterprise VHD. We download that VHD. Again, we attach a differencing disk. And this time, we also create and attach an application VHD. You, the application developer, have uploaded a package containing your code into the fabric, and we now download that package to the machine, extract the contents, and start your application. Let's start another virtual machine. This time, we're going to use server core, not server enterprise. We don't have that VHD yet, so we have to copy it. The rest of the steps are similar. We attach a differencing disk, create an app VHD, download the app package, start the app. Now, let's do a third virtual machine, this time with server enterprise again. Because the base VHD is read-only, we can share the VHD among the two virtual machines that are running server enterprise. The rest of the steps are the same, as you can see. This is very important to us. It means that we don't have to make a copy of this huge, and it really is huge, operating system VHD for every virtual machine. We can share the VHDs. Deployment in Windows Azure is essentially just Xcopy, as you saw on the last slide. We don't install or patch at target nodes. So deployment is very quick and very reliable. We can download in the background. Eric mentioned this on one of his slides, that we're booting out of an image. That image is a file on the hard disk. If we want to download a new version of the image, we can do that in the background by copying a new file to the disk. When it's there, we can reboot into the new image. And this minimizes the amount of downtime for the node because you're not down while waiting for the copy. We use a multicast transfer protocol that allows us, when sending an image to potentially thousands of nodes in the data center, to have that image appear on the wire only once. Image-based deployment allows us to cache images. They're just files on the disk. We can store lots of them, which allows us to quickly roll back. So we have the old version there. We copy in the new version, start up the new version. If there's some problem and we need to roll back, we can quickly switch back to the old version. As I mentioned before, we do servicing offline, so we know with certainty that patches are properly applied before we deploy the image. The Windows Azure deployment model, combined with the Fabric controller's allocation algorithms and oversight, allows for a dynamic allocation of instances based on your business needs. You can add and subtract images very quickly. The net result is higher availability for your service at lower cost. Okay, so I've been talking about virtual machines. What does a virtual machine look like? In the tech preview timeframe, there's one type of virtual machine, and this is what it looks like. It runs the Windows Server 2008 Enterprise Edition in 64-bit mode on the equivalent of a 1.5 to 1.7 gigahertz processor. It's got 1.7 gigabytes of RAM, and it has the equivalent of a 100 megabit per second network uplink. You have access to up to 250 gigabytes of local storage. But this is transient local storage, and we recommend not using it for anything other than cache-type functions. It's transient in the sense that if something happens to the node, it goes down, we can't use it anymore, we will reinstantiate the role instance that was on that node on a different physical node. And we won't move the storage, primarily because we probably won't be able to get to the storage because the node died. For durable storage, we recommend using the Windows Azure Storage Service. The full service model supports the ability for the Fabric controller to expose and for your service to request other types of virtual machines. But we're not exposing that at this time, and you can expect to see it later in 2009. Back to the hypervisor. The hypervisor, as I said, takes advantage of hardware advances. One of these is second-level address translation, which dramatically reduces the overhead of virtualization. Another is non-uniform memory access, which provides for fast access to processor local memory and allows the number of logical processors in a system to scale up without loss of performance. I'll talk about both of these on the next few slides. Our hypervisor is small. It's been stripped down to the bare necessities for our environment. If we didn't need it, we didn't put it in. We also have a low runtime memory requirement, largely due to second-level address translation, as I said I'll discuss. The guest OS is Windows Server 2008 Enterprise Edition in the tech preview timeframe. The host OS is Windows Server 2008 Server Core Edition with the hypervisor enabled. Using Server Core dramatically reduces the footprint, both static and runtime, of the hypervisor and the host OS. The host OS and the guest OS are tightly coupled to the hypervisor, highly optimized for our environment to maximize performance. The hypervisor, the guest OS, and the host OS combine to provide balanced I/O performance among the virtual machines sharing a physical host. No one virtual machine can overwhelm the other virtual machines on the host. We do this in such a way that overall performance is not compromised. We can get maximum throughput and bandwidth. In a virtualized environment, the guest OS sets up page tables that map guest virtual addresses to guest physical addresses. But these guest physical addresses are not the same as host physical addresses. An extra level of translation is required. In the absence of hardware assistance, the hypervisor has to manage this extra level of translation. This is typically done using shadow page tables, where a second copy of the page tables is created. The one that the guest manages is kept off to the side, and the one that the hypervisor manages with real physical addresses is shown to the hardware. Second level address translation helps with this problem by having the hardware understand this extra level of translation. Rather than chewing up a lot of memory with a second set of page tables, we can directly use we can directly have hardware have the mapping from guest physical addresses to host physical addresses. The CPU overhead of virtualization is dramatically reduced by second level address translation because the amount of time that the processor itself spends doing the translation is reduced. And we don't take as many page faults in the hypervisor. We also make use of large pages. Rather than using 4 kilobyte pages, we use 2 megabyte pages and even 1 gigabyte pages whenever possible. This again makes hardware translations more efficient and reduces pressure on the translation look-aside buffer, the TLB. In a non-uniform memory access architecture, the system is divided into groups of processors, or NUMA nodes. Each NUMA node has one or more processors and has some subset of the physical memory of the system dedicated to the processors in that NUMA node. All NUMA nodes can access all of physical memory, but there's latency if you go from one NUMA node to another. Here's a picture of what this looks like. In this picture, the first NUMA node, the top left NUMA node, can access memory within its own NUMA node very quickly. Access from the top left to the top right pays a latency cost. And access from the top left to the bottom right pays an even higher latency cost because there's a double hop involved. In the Windows Azure hypervisor, the scheduler in the Windows Azure hypervisor is NUMA aware. This allows us to scale virtual machines much better. The hypervisor assigns an ideal NUMA node to each virtual machine, and whenever it wants to allocate memory for that virtual machine, it tries to allocate it from that ideal NUMA node. If memory is not available there, the hypervisor goes to the nearest NUMA node that does have available memory. Similarly, the hypervisor strives to keep virtual processors, threads of execution, close to their memory. So when a virtual processor is ready to run, the hypervisor tries to find a logical processor that's available in that virtual machine's ideal NUMA node, and again goes to the nearest NUMA node if necessary. This leads to very good NUMA performance, as you can see on this slide. Or maybe you can't. It's kind of a complicated slide, but let me try to explain what it is. Here for this test, we ran the Web Fundamentals full mix workload. We ran this on a machine that had 16 cores, 4 cores in each of 4 NUMA nodes. We ran 4 virtual machines. Each virtual machine had 4 virtual processors. So we had 16 virtual processors, 16 logical processors, 4 NUMA nodes, 4 virtual machines. The 4 charts show the runtime of each of the 4 virtual machines, VM1 top left, VM2 top right, and so on. Each chart has 4 bar colors, 1 for each virtual processor in the corresponding virtual machine. The x-axis shows the 16 logical processors. The y-axis shows the amount of time each virtual processor spent on the corresponding logical processor. Now, for maximum performance, you want each virtual machine, each virtual processor to be running on the ideal NUMA node as much as possible. And that's what happened here. Virtual machine 1 was assigned to NUMA node 1 with logical processors 1 through 4. And you can see that its virtual processors ran almost entirely in that NUMA node. The same thing held for the other virtual machines. And not only that, you can also see that, that each virtual processor ran almost entirely on the same logical processor, thus being able to take advantage of per processor caches. In addition to the optimizations I've just discussed, second-level address translation, large pages, NUMA awareness, we have also made a large number of other optimizations in our hypervisor, in our virtualization model. I won't go into detail of all of these in the interest of time, but just point out again, as I said earlier, these changes, these optimizations are everywhere in the hypervisor, the VM bus, the virtualization stack, and the host and guest operating systems. Taken together, this gives us a highly optimized environment for virtual computing in the cloud. So, summarizing my section of the talk, Windows Azure's deployment model yields automated and reliable deployment. Our compute instance virtualization architecture features an efficient and scalable hypervisor that stays out of the way while also providing strong security and performance isolation. We have had, of course, several other sessions. I hope you've had a chance to attend some of them. If not, you can see them on the web. Our hands-on lab and our lounge are still open. Please come and visit if you haven't already. And of course, don't forget to go to azure.com and register. This is the obligatory please fill out the survey slide. And now Eric and I will take any questions that you have. Thank you. Please come to the microphones and speak directly into the microphones. Those of you who aren't staying, please exit quietly so that we can hear the questions and the answers. Over here, please.
Hello. The service model conforms to the Oslo visions.
The service model today is not based on the Oslo modeling.
I was wondering if it was an Oslo incubation.
Yeah, it currently is not, although we are looking at fusing the two and making them the same.
Thanks.
Yeah.
In the middle?
Yeah. I'm wondering why you don't make your infrastructure also available on the customer premises so that they could more dynamically offload some of their load into the cloud dynamically and as needed basis?
That's something that at this stage we're not prepared to discuss. We're certainly willing to take feedback on that.
Okay,
and
thank
we
you.
have gotten a lot. Over here, please.
You spoke a little bit about fabric controller failover. I was just curious if you could comment on some of the details, like whether the load balancing uses direct server return, or how you recover application data that was on nodes that have failed, or how any of these features work or don't work across data centers and across geographic regions.
Yeah. So right now we have a single data center for the CTP release. And additionally, if a machine fails, there's no guarantee that any state on that machine will survive, right? So part of the model is that either you have to take on a bit of a design burden to make sure that you're replicating state, or what we prefer most people to do is use our underlying storage where we've taken on that burden ourselves. It sounded like you may have had some deeper questions, so we can also talk offline if you need to. You can come by the lounge.
Over here.
Yes, at the beginning you talk about SLA in the fabric. Can you give us some example of this SLA management?
Yeah. So currently in the CTP release, we actually don't have any SLAs, but we know we need them. I don't think anybody would trust putting their service in the cloud for real if they didn't have any guarantees about availability or that sort of thing, right? So we don't have the specifics. Part of what we're going to do during the coming year is nail down our business model. You know, we want to get feedback from you guys, but nail down that business model and start nailing down what those SLAs would be. So any feedback you have would be welcome.
Thank you.
First, quick question, just out of curiosity. Is the Fabric controller written managed code, or?
Most of it is in managed code. That's correct.
And then with server instances, so if I say I need 4 instances of this particular role, can you have individual configuration elements per instance? Is
Yes.
that supported? Okay.
Yes, you can.
You mentioned your ability to track service failures in the environment. At what level of granularity do you have that ability? You know, is it just physical or VM failures or service failures? You know, how granular can you be?
In a sense, all of the above. Although, let me, in the CTP release, there is something missing, right? So it's possible in a real service that all of the machines are running, all of the code is running, everything is bound together and connected correctly, and the service itself still isn't working properly, right? I mean, that's possible. In this release, we can't detect that scenario. We don't have a tight enough coupling where we communicate with the role so that you could tell us, for example, that things aren't working. But what we can do in the CTP release is we can notice the failure of any individual role instance or the hosting environment hosting that role instance, right, or any other networking infrastructure. So we have 99, well, a big piece of the puzzle, but we don't have that last piece where the service itself at a global level could say, I'm healthy or not healthy. That is coming.
Oh, that's coming. Okay.
Yep.
There was an article that was just released that Dell DCS has manufacture all the Azure hardware. I was wondering if you could comment on, is that going to be containers? Is it,
I'm sorry, could you say that question again?
yeah, there was an article just released that Dell DCS has exclusive rights to manufacture all the Azure hardware. Oh, can't hear?
That is news to me.
Yeah.
I'd have to read the article before I could comment further.
Could you comment on the load balancing at all? Is that all software based or is it hardware based?
We have hardware load balancers today. Yeah. We'll continue to evaluate what makes sense or maybe offer both, but for today it's hardware load balancing.
Yeah, I'm still continuing to work under the current application lifecycle model and the current RDBMS model. So I'm just curious. It's kind of a smaller concern, I guess, but I think the presumption that you're using is that an application upgrade would occur like in one shot. But what if we need to? Are you accounting at all for application offlining, like the maintenance window, if you will, where say we actually do need to reform our database schema? I know SDS is not supposed to use schemas, but again, I'm still working in the old model. And the way it works right now, I could see a scenario where we might have to take our application offline, reform our schema, which under what SDS provides could take minutes perhaps, and then bring our application back online. Is that thing handled?
Yeah, so this is actually a good question. So there's nothing magical about the upgrades. And in a schema if you're upgrading the service and that requires a schema upgrade of data at the same time, clearly that's more complicated, right? So we can talk offline and about how those things work.
Thank you.
The discussion I did in here is the more simpler bug fix or adding a feature upgrade. Yeah.
Regarding the hardware, I saw that you said you picked a certain processor speed level, and I was also wondering how other factors such as cache size of the processor, front side bus, and memory speed, how they all kind of fitted in terms of the puzzle of you trying to optimize what you get out of the platform for the price. And also the issue of the newer processors keep lowering the wattage consumption and how that's factoring in.
All of those are factors that go into that we take into consideration. The specs that we're publishing are what you saw, at least in the tech preview timeframe. But certainly we take all of those things into consideration when we're looking at hardware, when we're trying to optimize our hardware and our software. We're looking very much actively at the lower wattage processors that are coming onto the scene. We want to reduce our power consumption.
I don't know, did your thing show the other like cache size and front side bus in terms of you trying to optimize this mix?
No, we didn't publish anything about that, no.
And what are those kind of values you're using on this platform today with your processor speed? Are you using the biggest cache size or the 1333 front side bus or what?
I think this question is best taken offline. So come to our lounge, or we can talk later. In the center.
Yeah, the examples of resource allocation for scale-up that I've seen have all been manual, where you go in and you change your config setting for, I need 6 nodes instead of 5 or whatever. Is the plan, though, to make that more dynamic as part of the SLAs, where you can just say, I need this thing to always be available, and you'll just dynamically provision additional nodes as needed?
So the underlying service model that, like I said, we don't fully expose to you today, actually lets you specify not, this is what I need, it lets you specify a range, right, which provides the Fabric controller some freedom in what it gives to you. We do actually have aspirations for doing exactly what you said and dynamically adjust the instance counts to meet the needs. We don't do that in the CTP release, but we're looking at that down the road.
I had a question about the 50 gig the durable storage. Is it visible to the guest partition?
What is available to the guest partition? Is that
the 50 gig durable storage.
The 50 gig of durable storage is in the Windows Azure storage service. It's off-node. It's in the Fabric, but it's not on the machine.
But the guest couldn't see it.
The guest can see it.
Like in what form? Is it like an iSCSI?
Oh, it sees it via a runtime API calls, basically. Right.
Over here.
So I had a question. You described that you're managing the OS update process. Now, clearly you're doing that for the host operating system. In the guest context, does the user end up having control over the OS plane?
The answer is no. We actually manage it for both the root and inside of a VM, right? So we don't actually expose to you virtual machines directly. In fact, it's kind of an implementation detail. Probably not likely to change anytime soon, but it's kind of an implementation detail. You basically just describe what you need, the environment, what the hosting environment should look like, and give us the code. And then we build up that environment and run it there. And then we may have to stop your role for a period of time so we can update that OS under you. Right?
So any of basically I don't have any control over the dependencies on the underlying OS.
You do. You can describe them as part of the service model.
And then you would pin the OS according to what I need?
Essentially, yes.
Well,
depends on what you mean by pin.
Talking about, if you're talking about what components you need in the operating system, you will in the future be able to specify in the service model that you need IAS or something like that. But in terms of updating the OS, which particular version of the OS, At the moment, we're not planning to expose that to you. Certainly for security patches, we're going to put those in when they're needed.
That seems to have some pretty serious implications for qualification of the service.
We understand that, and as we move forward, we will address it. We've heard that loud and clear.
Yeah. If you want to come by the lounge later, we can give you some insights of what we've been thinking about.
Thank you.
In the middle.
If I'm using Windows Azure Storage as my persistent store together with my application, what kind of latency can I expect from that? Is it a single millisecond range, or is it more than that? Because that's going to change how I have to think about how often I'm kind of persisting.
Yeah, I don't know if we've specified that. That would be part of the SLA, and as we've said, we haven't defined the SLA yet.
Thoughts, I mean, in practice today, what do I expect?
The storage folks might have some answers to that. I don't think we do.
Come by the lounge. We'll hook you up with the right storage service person to answer that question.
Thanks.
Do we have one over here? No. Okay. Thank you very much.
Thanks, guys.